did his undergrad studies in Tongji and then his PhD in geotech. And he has visited several really impressive physical modeling centers, such as in Hong Kong or University of Western Australia. And since about 2 years ago, he's a postdoctoral researcher at TU Delft. And in January, he's going to NGI, to Norway. And he's going to talk about offshore foundations. Juan.
Thank you, Amin. Okay. Sorry. Just one moment. Something is wrong. Just okay. 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 Hi, everyone. Thank you, Amin, for the introduction. I'm Huan Wang from TU Delft. So today I'm going to give some example of the application of physics modeling in the offshore geomechanics. And before I start, I would like first to thank you, Amin, and our PhD student Tristan, because most of work was a teamwork between us. So okay, so the presentation today will mainly focus on the monopile foundation. And from the installation of the pile to the influence of the scaling on the behavior of pile, and in the end, I will present some recent work on the long-term behavior of the pile foundation. So some brief background. I think as you all know, like we are in the middle of this energy transition, and we are developing renewable energy a lot. And among that, the offshore wind energy definitely going to play a very big role. And in Europe, we set a quite large target, and this target is keep increasing almost every day. And so for the offshore wind turbine, currently almost 80% the offshore wind turbine are built about using the monopile foundation. And as you can see here, the monopile foundation for offshore wind are subjected to the large cyclic load from the environment, like wind, wave, and currents. And also because the offshore wind is quite unique, it's a very long, tall, slender structure. So we have very strict design requirement for the dynamic behavior of the structure. So we really need to know what's the foundation stiffness at very, very small deflection. So and all the work was performed using the using the centrifuge at TU Delft. So you already see a lot of centrifuge in this series of talks. And at TU Delft, we also have a centrifuge. We have quite long history using centrifuge since last 90s. And our centrifuge is relatively small, but is very efficient in terms of preparation and to validate some ideas. And the maximum payload is 300 kilogram, but at 300 G, that's the maximum. But we never go that far. And the maximum, I think we went to 150. And the nominal radius is around 1.3 meters. And the good thing is we have a lot of logging channels. In total, we have 48, which is very important for centrifuge modeling because that basically controls how many sensors you can install and how much you can know for your test. And the centrifuge has been used in many applications like offshore engineering and dikes, piles, earthquake also, and surface subsidence like a settlement. So back to the monopile foundation, I think the first thing we need to consider is, okay, how are you going to install the monopile foundation? Because the monopile is quite different from the old piles because it's very huge. The diameter can go to 10 meters in nowadays, and people are talking about 15 meters. And the embedded length is quite shallow, and it's around like less than 5 times the pile diameter. traditionally people install the pile foundation using this hammer system, and it's not a problem before for example, oil and gas platform because you don't have so many pile foundations. But once you come to the offshore wind farm, certainly you are going to install hundreds of monopiles. So then you need to think about, okay, how can I improve the installation, because that's basically money related. And before I go to very scientific part, actually in our daily life is quite similar something like you are hammering a nail inside a wood. And this very simple video kind of already tells us what we need to do about the installation of the hammering system. You can hammer at different, using bigger hammer, you can hammer the nail with a very high frequency. So that depends how much the nail can penetrate inside the wood. And basically, that's what is the mechanism also for the installation of the monopile. You have a hammer here, as you can see on the right, and there is a big mass. First, you lift the mass, then you have the potential energy stored in this mass, and then you release the mass, and the whole mass will hit on the anvil. But remember, because the hitting, there will be some energy lost in between the hammer and anvil. And through the anvil, the energy will further transform to the pile, and push or penetrate the pile inside the soil. And between the anvil and the pile, there is also some energy loss. So there is something we can do to improve this whole process. For example, back to this hammer of a nail, I think in our daily life, I don't know if you have the experience, if you hammer the nail in something very stiff, there is some bouncing back, and sometimes you just put a very soft material in between, then you hammer again, and it can penetrate easily. So this kind of idea can also be used to optimize the hammer system. And at TU Delft, I think yesterday Luke already showed you some hammer system developed in France. And in TU Delft, we also have a hammer system developed in-house. And as you can see, we use a different mechanism. And this is inside the hammer. We have a called like flywheel, which will lift the ram mass. And by control the rotating speed, you can control the hammer frequency. And there is the gear system to control how fast this flywheel can lift. And this whole setup will move together when the pile is penetrated to make sure we always has a constant penetration hammering distance. And this is the anvil. And on top of the pile, we also have some special design part which can help us to have a laser system to basically against this thing and tell us how much we really penetrate the pile in. And this is basically the idea of this whole setup. And in this video, we show you how this works. It lifts the ram mass and the pile penetrates. The whole system follows this pile, and we keep a constant hammering distance. And here I show you two tests, and basically because the video from our PhD student Tristan is very nice video. On the left is kind of like a single below test. We lift the ram mass, we penetrate, and we just want to understand how the pore pressure generates around the pile, and how this will affect the penetration depth. And on the right, if we play again, it's basically a very fast hammering at a frequency around 25. So basically, by looking into the hammering frequency, we can kind of more optimize this whole pile driving procedure. And when we look into the performance of our hammer system, you can see like when we check the pile penetration and the whole movement of the hammer part, they basically follows exactly, especially on the left, the difference of the whole motor and the pile movement almost collapse. So it means we always keep a constant hammer distance. And on the right at the beginning, there is some like delay of the motor, but at very large penetration, we can see they all still work quite well. And so when we penetrate the pile, we also put some pore pressure sensors inside the soil to understand what's really happening and at different depths and different distance. And on the left, you can see the response of pore pressure, like when you penetrate the pile inside the soil. And when the pile tip is reaching the sensor, you can clearly see the increase of the excess pore pressure. And on the very left is the sensor at the pile tip. And when the pile is penetrating, especially when it really reached the depth of the sensor, the pore pressure increase. So in this, we can really understand how this whole penetration will generate the pore pressure and the influence of the soil state. But the thing is, the traditional pore pressure sensor is very large. We can only instrument at certain distance, and we don't know what's really happening very close to the pile. So that's we use this optical fiber pressure sensor. I think Suzanne in the presentation already show you. But the good thing is it's really tiny. It's like a hair. So you can instrument this sensor along the pile to really capture the pore pressure response at the interface. And if you look the results in the next slide, you can see we plot the response from both the optical fiber and the traditional pore pressure sensor. And during the acceleration of the centrifuge in the test, after the centrifuge test, you can see the optical fiber can really capture the pore pressure response. And this, in the between, we start the hammering, and it also can capture this dynamic change of the pore pressure. There is some difference between the static pore pressure and this optic fiber. This is mainly because you can imagine this whole pile penetration is really a dynamic response. So the response of the pore pressure at the interface is really fast. And at that time, our logging system for this optic fiber is not that fast. So we didn't really capture it, but we already improved the logging system. So in the future test, we can really capture what's happening at that moment. And as a follow-up of that work, we are currently working a industry joint project called blue piling. Basically, our industry partner developed a new concept of the hammer, and we want to test it in the centrifuge. And this project will involve both the interface test and numerical simulation, and the centrifuge test, and also the field test. So in the end, we will come up a new installation hammer system, and also to develop a new like pile soil interaction model to really simulate the whole installation process. And currently, our student Tristan already optimized the old hammer system, and we already have a new electronic mechanical actuator. And the thing is, compared to the traditional hammer, what we do here is we put a small buffer, if you see the right, between this ram mass and anvil. So this is kind of like simulating something soft. Then you can maintain longer interaction time between the whole system and the pile. So basically, with this concept, I show you in the next slide. Sorry. Yeah, here you can see this is the numerical simulation results. We're using two different ideas. After you have a small buffer, you will have more the energy. Energy is almost comparable, but the interaction between the RAM mass and anvil is much longer. So you have more less like bouncing back, this kind of thing. So it will improve the penetration. And even further, we also developed specifically a hammer system called the blue piling actuator. So basically, in between, instead of a buffer, we also put this linear spring to even simulate more, to eliminate more like bouncing back, to make sure we have more interacting and more energy transformed to the pile. And with this, another good thing is we can decrease the noise during the installation, because in offshore you have a lot of creature around the pile. If you use a traditional hammer, normally you will see a lot of fish blowing around the pile after installation, because that really kills the fish. So we want to improve that also. And here I think just one moment. Here you also show the same concept, because using this new concept of hammer system, we can have different kind of energy transforming system results. And this project is undergoing, and I think there will be more results published, and maybe next year we will give you some updates. So next topic will be about the scaling of the monopile, because the monopile foundation will sit there for like 20 or 30 years, and because of the pile foundation, you certainly change the flow of the seabed, and there will be scaling happen. And I think Yannis already showed you some example and did here on a section occasion around the scaling. And at TU Delft, we also studied how the scalding will response of the monopile, and we did everything in the centrifuge. And here is basically a setup we are using. We have a loading system, and the pile has a dimension of around 90 millimeter in the length, and the diameter is 18 millimeter. It's a very typical monopile with a spectral ratio of pile. And here basically we studied different kind of scoring condition. You have on the right, we define certain score condition. We have very shallow score and different depths. We can also have very wide score, and even worse sometimes, because the score is so severe, the whole soil maybe just be taken away. So we study how these different score kind of shape will affect the later response of the monopile. You can really see the significant change or degradation of the stiffness and the capacity of the pile. From the left, the top, it's a narrow score, and you can see when we change from the narrow to the wide and to a global score, the capacity at around 0.3, if you see the displacement, is more than half of the capacity are lost. So this really something to consider when we design the monopile. And apart from that, we also did finite element simulations. Just a moment, it's a little bit slow. Okay. And so we also performed the numerical simulation to back analyze the centrifuge test results, and using our validated numerical model to further do more parametric study, and also really we can look in using the finite element model, we can look into what's happening between the soil pile interaction, like the PY curves. So this is also something undergoing in our project. So in the end, another important thing about the monopile is long-term behavior, because as I mentioned, the design of the monopile really brings a new challenge for us, because the design requirement is so strict. It requires the natural frequency to lie in this small narrow range between 1p and 3p, as you can see, it's 0.2 and 0.3. And in the real case, actually, the design company requires the prediction with like 10% difference with your target. So this is really tiny error there for you to play. And also we require like after 20 or 30 years, the maximum rotation of the whole system should be less than 0.25 degrees. So it's almost nothing if you measure this. So we really need to understand what will be the monopile response under such long-term cyclic load and such complex load. And that's the motivation of a project we are doing called Midas. So it's an industry joint project. As you can see on the left, TU Delft together with the Terrace and a lot of companies in the offshore wind industry, we are trying to tackle this difficult problem. We are going to combine both physical modeling and numerical modeling and element test. In the end, we are going to develop a new design model for the monopile, and our industry partner will implement that in their design guideline and to really use that design offshore wind turbines. And in this, you can see is basically an idea of how we are really going to do this project. So we use the element test to understand the soil behavior under long-term multi-cycle loading. And we have already developed also a soil constitutive model to simulate the long-term behavior of the soil element. And also at TU Delft, it's quite unique is we have a small centrifuge, but also like with 10 minutes walk at the terrace, we also have a huge centrifuge. I will show you later. And in the end, we are going to develop a new design and model for offshore wind monopiles. So in this project, we are going to use 2 centrifuge. At TUDEF, we have the small centrifuge, and at the Taurus, we have quite new centrifuge and quite large with a radius of 5 meters. So we're using these 2 centrifuge, as you can see on the right, we can really play a lot with the dimension of the pile. And in the end, we can monitor modeling the prototype diameter with from 1.8 to around 13 meters. So basically, beyond your imagination, like I think all the monopiles can be used for offshore. We already kind of covered. And so what we did is, on the left, I show you a figure, basically what's the monopiles there. As you can see, the green dots, but that's between before 2017. And I think a recent year it should become much larger diameter, and the aspect ratio decrease. Basically, our modeling case covered all the possible case, and we performed quite many tests in different density sand, different pile configuration, and both saturated and dry sand. And on the right, I show you a typical contour of the cyclic load on a 14 megawatt offshore wind turbine. And based on that, we designed our centrifuge test program to really capture what's really happening in the field. And we did quite many tests, as you can see, more than like 50 cyclic tests to really understand this. So this is a very short video show you how the centrifuge at TUDEF is running. So it's we prepare it at 1G, and at 100G is really spinning very fast. And we can apply our cyclic loading and read all the data from string gauge, the force displacement, which can allow us to back analyze the results. And here is the typical result of at the terrace. Maybe one thing to point out is, as you can see, for each centrifuge, you always need to design the setup, as Hoff already, I think, mentioned yesterday. You really need to figure out how you are going to apply the load, what kind of instrumentation you are going to put, what kind of thing you want to measure. So this is the typical setup for the monopile foundation. And also in the centrifuge, you can also characterize your soil with this mini CPT, which is very typical to in the field using CPT. So with this, you know the homogeneous of your soil, and you can also use the CPT to develop CPT-based design method for the foundation. It's a little bit slower, yeah. So in this project, I instrumented quite many piles. And in total, you can imagine, I think I instrument more than 400 or 500 string gauge. That's really a big fun. And also one thing to mention is, on this pile, you can see here, we instrument not only the string gauge, also small soil pressure sensor on the pile. So you can really get what's happening between the pile and the soil. It's really nice work. Okay. And here is the video shows you, like, we put 3 piles in the centrifuge and we load it cyclically, one by one. And this was performed in a saturated soil. And you can see the whole actuating system works perfectly. Okay, so what we are going to do with all the data we have here, I just show you some results we have and just give you a taste. First, what we can do is, okay, we have design guidelines, we have existing design models for the monopiles, and the most widely used method basically is to simplify the pile as a beam, and you simplify the soil as springs. And there is already some equation in the design guidelines, but people already question, like, those model seems not working when they really do the design. And there's also a lot of model which using the measurement from the field to develop this called CPT-based design model. And what we did is, okay, we just evaluate how accurate are these models. First, for our test, at these 2 typical tests, it seems the design code first is not good. We will definitely need to improve that. And for all the other CPT kind of based design model, it seems all the model somehow capture the initial response, but when we really goes to large deflection, the prediction becomes less. And this is only 2 typical cases. And if we include all the simulation case, you will see that there's no one model can predict all the results. So we really need to improve that. And another thing I think Miguel also mentioned a lot is like, okay, we can come up with some simple non-dimensional results, which maybe not completely right, but it's very useful. So for the monopile, we did quite some numerical simulation and come up with this. On the right is very simplified pile-cell interaction model. And with this, you just play a little bit with like a force on the moment equilibrium, some mathematical work, and you will come up this right equation. Basically, all the pile with different diameter, different length, loading different height can be unified with this left equation, and they become a unique function of the rotation. But this is only this is very simplified, and we don't know if it really work for the test. And what we did is, okay, we just analyze our centrifuge test data with that equation. On the left, you can see the absolute measurement from centrifuge against the rotation. So you can imagine when the pile is larger and the embedded length is deeper, the reaction force will become much larger. But when you apply our normalization result on the right, you can see all the results can be perfectly converged to a single line almost. So this kind of thing is really helpful to people to design their tests. Even, for example, people using just the 1G large scale test, they can use this kind of normalization to get what really happened in the prototype, large diameter. And more importantly, we even plot more results within this result. And you can see the test performed at different pile in both dry sand, saturated, and also on the right, we have the results from the literature. Completely different sand, different pile, but the relative density is quite close and they really collapse to each other. So at least for a uniform sand, we have very good normalization results, which can help people to analyze the results. Another thing related to the offshore wind is the drainage condition. Basically, offshore is always saturated. So what will be the drainage condition? So we also perform tests in the viscous fluid saturated and water saturated test, because if you use viscous fluid, you can imagine the drainage is much slower, then we can more close to the field. And we also put the pore pressure sensor at different depths and different distance to the pile. And first we did a completely almost like a drain test in both in the water and viscous saturated soil. There is some minor difference because the density is not exactly the same, but as you can see, when it is drained, you will get very, very close results. Basically, once it's drained, you use viscous fluid or water, doesn't matter, it will give you, it's completely effectively stress controlled. But then, okay, and also this is also confirmed by the measurement of the pore pressure sensors. I won't go to detail. And then what we did is we did some cyclic tests, as you can see, for tests both in water and viscous fluid saturated soil, and at different displacement amplitude and different frequency. And what you can see is on the left is the pore pressure response in the water, almost nothing. It's very, very small. And on the right, there is more reaction or more response from pore pressure. So there is excess pore pressure generated. But another thing, interesting thing is, I think compared to what we observed in the seismic test, in the seismic test, you will observe a quite large excess pore pressure at the beginning, then they maybe with test it dissipate. But here you really observe it's very transient oscillation pore pressure. There is no accumulation. So there is some partially drained response, but it basically means all the response is mainly controlled by the drained behavior.
Sorry, I don't want to interrupt, but
yeah.
Is it 0, 1, 0.5 and 1 hertz prototype scale or centrifuge?
It's in the centrifuge scale. It's 0.1 hertz and 1 hertz at centrifuge, in the centrifuge.
So a model scale?
Yeah, it's model scale, yeah.
Okay.
We did some calculation, I think, because for us, it's not that dynamic, so it's consolidation related. So even we use viscous fluid, we still far slower than the field. But the good thing is for the offshore wind, the normal frequency is around 0.1. So we are about like 10 times slower. But here we use displacement control to even apply force very fast, so make our results more close to the field. Yeah.
So in prototype, how much is it?
Prototype is normal like 0.1 hertz.
0.1 hertz.
Yeah, for a typical wave.
So it's quite slow, let's say.
Yeah, it's quite. Of course, if there is storm loading, then that's maybe a little bit larger. But in the normal case, it's 0.1. Yeah.
Thank you.
So basically, the observation we have is, okay, most time the response of monopile is controlled by the drained response. There is small and drained response, but not that important. And okay, the very last piece is basically, okay, as I said, the response is mostly drained, then you apply the load, the soil will contract, then you have deformation of the pile. So we started also all different kind of cyclic load, as you can see on the left, different amplitude, then you have the accumulation of the rotation. And also we change the sequence of the load, then you can observe a completely different final accumulation. And then we are developing model to really capture this long-term accumulation behavior of the monopile. Okay, a very last, basically, I only show you some application of the centrifuge for the monopile, but actually you can do much more using centrifuge. This is a very nice figure. Basically, using centrifuge, you can study the foundation of the platform, you can study the pipeline system, and also the anchor, everything. And more importantly, I show you the bottom fixed offshore wind, but the future we believe is maybe more like will be found by the floating type offshore wind turbine. Then you have the anchor system, and we also have the floating like offshore solar plant. Then so there is a lot of things you can do in the centrifuge. And I think later Professor Mac Brown will give you some presentation about like what our as a geotechnical engineer can contribute for this future offshore floating wind turbines. So that's all for the presentation. Thank you.
Thank you very much, Juan. Miguel, I don't know we are good until 2. And 3 we will have coffee or good. Okay, so we have 7 minutes for questions. Eva.
Thank you very much for the presentation. Could you please go to slide 28? Oh, maybe it's one before that. It's a photo of your model monopiles, I think.
Here.
When they were installed in the center.
This one?
No, the monopile. When they were installed in the model.
Ah, okay, here.
Yes, that's it. So, have you facilitated an interface? I suppose the monopile, the material is aluminum, or right? Have you taken into account an interface for the monopiles? And if yes,
yes, thank you. Yeah, because in the centrifuge we need we instrument strain gauge, then we put epoxy to protect the strain gauge. So we will have a different kind of interface between the soil and the prototype or aluminum pipe. But for this epoxy, we did some interface test before. The friction angle is different from the aluminum, but it's quite close. And also for the lateral response of the monopile, we also did some numerical simulations. The influence of the interface roughness in that range, even a very big change doesn't really affect that much the lateral response. But I guess if it's vertical loaded pipe, it becomes more important. Yeah.
And those were also hammered in, or were they wished in place?
Yeah, for the test at the terrace, we do everything in the wish in place, because we, of course, first we don't have a hammer at the terrace, but more importantly, we want to develop a numerical model to validate the centrifuge test, and that's a little bit better to have better control of the soil if we do it by wish in place. So if it's hammering becomes a little bit complicated, then that's the next step. Yeah, for the numerical to validate. Yeah.
Okay, and there was when it was further along in the slides, you don't have to go there, but you mentioned something between simulating drained and undrained conditions in the centrifuge experiment, and you were using water for saturation fluid and viscous fluid. Could you please explain this a little bit better?
Yes. So
yes, how do you facilitate the undrained conditions?
Yeah. So because we use the viscous fluid to decrease the dissipation speed to try to mimic the offshore wind turbine, try to capture what's really happening to the drainage condition. And before doing that, we kind of want to know, okay, if the difference of fluid itself, for example, if you use viscous fluid instead of water, will affect the response. And what we control here is basically we load the pile very, very slow to make sure it's fully drained condition. And then it shouldn't be matter what kind of fluid you use. And then that's the results we have. Like you can see here, they are really close. And there is some difference because of the rate density, but they are really close, which means the fluid, like the viscous fluid itself, won't change the mechanical behavior of the sand. Then following that, we go to the cyclic, then we study the drainage condition. Yeah.
The viscous fluid is of the proper G level, right? So it's at 100 CP.
Yeah, all the tests were performed at 100 G, but the viscosity is 100 times larger than the water.
Right. And then for the cyclic part?
For the cyclic part is still same 100 times viscosity, and we did displacement controlled cyclic at different frequency. And then you can see because of the viscosity or because of the drainage condition between water and viscosity, and viscous fluid, you can see the response of the pore pressure. On the left, it's almost fully drained. You don't observe any variation of the pore pressure.
Both drain.
On the right, I agree. So on the right, there is a little bit undrained because we have this oscillation pore pressure, but very, very minimum. That's actually good because we want to kind of justify our judgment at the beginning. We think it's fully drained, or the monopile is more controlled by the drain. But people say, okay, they did a numerical simulation. They said it's not the case. Then we did the centrifuge test, and as you said, it's really almost a fully drained condition. It is very tiny and drained, but it's very limited.
But this is because your cyclic loading is, let's say, relatively slow.
Yes, in a way, yes. But another thing is, you can imagine in the field, it's more like a load-controlled condition. You have a wave and wind. But in the centrifuge, what we did is we applied quite large, and for this, we also did load control. But in this case, I show you the displacement control. So as you can see here, we really pushed the part to a very large displacement at a very high speed. And so what we are doing here, even maybe is more faster than what's happening in the offshore. So even with this case, you don't expect that much pore pressure accumulation. So we think in the field it's even less maybe.
But I'm a bit puzzled because in reality, the period of waves is something like what is it, like
10 seconds or something?
10 seconds, let's say, right?
Yeah.
So
I would not say that this is very slow. I mean, in reality, you also have 0.1 hertz more or less as a typical loading.
In reality.
Yeah, in reality, yeah.
But 0.01 hertz would be 10 hertz in the census, no?
We did the test at 50 G, so it's
yeah, this one is 100. Yes, yeah. So if we scale that should be 10 hertz, and we did only 1 hertz here.
Yeah, because it's difficult with actuation.
Yeah. So the good thing, as I mentioned, with that scaling law, we're still 10 times slower.
10 times slower than what the waves would be, right?
Yes. But we do it by displacement control. So the response of the load actually is even faster than that. So we are kind of compared to the field. Yeah. So that's the observation.
Also, one point is about the location of the pore pressure transducer. So these were, I believe, one radius away from the pile, and the next generation of measurements would be using the optical fibers, which are exactly installed at the skin of the pile. So over there, you can have a better observation of the pore pressure generation.
Yeah, that's a very good point because we put the pore pressure sensor around 1 pile diameter away, but as you can imagine, when you're close to the pile, the soil deformed more, so there may be more response of pore pressure. But it's the centrifuge test. We didn't have time at that time to instrument the optical fiber. But we are going to do some numerical simulation to kind of quantify, okay, how much this will really affect the power response.
Mike?
Thanks, Juan. The work you're doing with the blue piling, is that in sand? And what is the main aim there of that study? Is it to optimize the loading duration or predict, what you're going to need to drive in different soil types?
Just one moment. Yeah. This is okay. Thank you, Mike. Yes, I think this one, our test was it will be performed in sand, and the motivation for this is because the industry partner come up with a new hammer, which basically instead of using a steel as the ram mass, what they are going to do is they put water inside this whole chamber. They hammer the pile, and which will generate completely different, like a false signal, as I show you here. Just one moment. Yeah, here, like if it's a steel, it's very the stiffness is very high, and there is bouncing back, so you can see the false with time is very sharp. Okay, this is good one. So this black curve, and what the blue piling is generating is the energy is still comparable, but you can see the curve is much like a wide, and and it will generate less noisy. And they try to see if it will get the same efficiency in terms of installation of pile, but generate less noise. And in the end, maybe that's a good direction to go for the offshore.
And I think then obviously the following question is then what happens if you go into clay?
Yes, I think that will be a next topic. I guess we want to check, but in clay, I guess it really depends on what kind of clay in the offshore. If it's very soft clay, I think what we worried more is more like a pile running instead of really hammering the pile in. But if it's really stiff pile, yes, then it may be not that efficient, but we need to look into in the future, maybe. Yeah.
Because I think the pulse is a statnamic test. That's where the concept came from, which is what I did my PhD on in rate effects. So clays is the fun bit. 3 times as much strength as static clay behavior at those kind of speeds. So it will be fun.
Yeah. Thank you.
Indeed. One addition about the gray curve that we see here. We see that the integral of basically the energy between the 2 piles in this case is comparable, but the company IHC has foreseen to actually increase the energy by a factor of maybe 1 order of magnitude to basic, but still prolonging the pulse to about 200 milliseconds, so around maybe 20 times more than the impact hammer pulse.
So you maintain the pilot compression, which is the concept of standard pulse.
Exactly.
So Rob at IHC was the standard converter, so we just converted it to the pilot.
Yeah, indeed. Yeah. Yes.
Yes. So thank you very much for because good presentations are also very motivational. So I want to ask your opinion about something, about the slide with the API method that we want to develop. So you said that most of the methods that they are there, they have some problems and they don't always can capture the response. And my question is, like the monopiles have the peculiarity that they are not slender piles, so we have L over D dimensions equal to 5 to 6, and with extremity the solve also equal to 3, which is much closer to the caissons. And so for caissons, it has been solved that you cannot capture the response if you don't include the rotational springs and you have only linear springs. And I understand that most of the methods they try to have only linear springs for simplicity, but it seems that without the rotational spring you cannot capture. So I wanted to ask from your results if you have seen that as L over D is getting smaller, you have more difficulty in order to capture the response. This is my question.
Yes. Okay. I think this question can be answered by 2 points. First, the lateral soil reaction, basically this PY curves itself actually change with the power expect ratio. Or basically, if you check this design code API, it was actually proposed for a very, very small diameter cylinder pile, like maybe 50 years ago. And now we have very large diameter, very short pile. So the pile configuration completely changed, the mechanism changed. So even you don't consider the rotation spring or all the other components, the PYS model itself, it doesn't work. So people should improve the PY model first. But as a follow-up of your question, yes, when we get the PY right, when the pile becomes much shorter, it becomes kind of like cation. Then you have the contribution more from the base, from the shaft friction. And at that moment, we need to add further like a new components like this distributed spring and base spring. And based on some like numerical simulation for the monopiles in sand, even with an aspect ratio of like 5 or 3, the contribution from all the other components is still around like maybe 20 or maybe a little bit more if the pile is really very large or the embedded length is really short. So most times still the PY curves contribute most. But if in the future we really go to that large and that's short pile, we need to incorporate all the other components. And that's already as part of this project, I think, our design method called PISA. So that's the answer, yeah.
One last question, if there is. Yes.
Which material model do you use for your numerical calculations?
Yes, for the MIDAS project, we are looking into the long-term behavior of the pile. So we really need to have a model that can capture the response of soil element after like hundreds of millions of cycles. So at UDEF, we already developed a model called Sandy Sand MS, which is based on the Sandy Sand framework, but we incorporate the memory surface to capture the long-term behavior of the sand. I think it's already published. If you're interested, you can check the paper. Yeah.
Yes, one very last question.
Just connected to these.
Yes, go ahead, please.
So basically, you said that you are going to incorporate the memory surface on the model. So my question is, have you observed in your experimental test a significant change in the response of the sand during the first cycles of loading? Because I imagine that if you need a memory surface, it's because you have seen an effect in the fabric of the soil.
Yes and no. Yeah, we can't really observe the change of the fabric because that's a different scale, of course. But from the response of the pile, you can clearly see the accumulation of the pile, like the rotation. You can see after many cycles, it keeps tilting, which means the soil must contract and fabric is changing. That's why you really need a model that can capture such many cycles. Yeah.
And what about in terms of stiffness? So
the stiffness also changed, but depends on what kind of stiffness you are talking about. So if you look for each cycle, there is a loading stiffness. If you only focus an individual cycle, you will observe like at the beginning there will be some increase, but after certain cycles, the stiffness doesn't change that much. But you see still the rotation keeps accumulates. Yeah.
And this not 3D analysis, 3D modeling.
Yeah.
And can you tell us about the time that it takes to calculate composite cycles?
I personally can't because that's a separate work. But I think for 100 cycles, it normally can take quite many hours, like 12 maybe or 1 day for 100 cycles. But we already implement this model in Plexis, which I think will take around 3 or 4 hours for 100 cycles simulation.
I have a question. Do you have an idea about what is the influence? So my question is, what is the influence of the installation effects on the long-term behavior of the monopipes?
Yes, that's a very good question. In our project we don't consider the installation effect. We do everything in wish in place or hijacking at 1G. But in the next step, we are planning to do some tests to really investigate that. And there is a separate project called the GDP, which investigate different installation methods like a jacking, vibering, or hammering, or there is also a torque combined with hammering, which is developed for that project. So you really look into how different installation methods will affect the later response of the monopile. There is some numerical work, I think, try to do it pure numerically. You can see if it's wish in place, you have more accumulation of rotation. But if you simulate the impact driving, the rotation will decrease. So in that case, yeah, I would say like wish in place is kind of a conservative way to study, but we are going to look at that in more detail in the future. Yeah.
All right. Thank you very much, Juan.
Thank you.
It was very good discussion. And now we have